Yeah. So I'll talk about some work I've done together with Mickaël Chekroun from the Weizmann Institute, and some of you know him, and I will refer to work done with other people, including someone in this audience. So the idea was, the overall idea is the following, the idea was to try to find dynamical basis of optimal fingerprinting for detection and attribution. So as you know, this is a massive sort of pillar of the behind the climate change science in general. So optimal detection and attribution techniques have allowed us to say, A, that climate change is real, and B, that it can be attributed with a high degree of certainties to anthropogenic forcing on top of the basically natural causes, and sort of singling out the signal from the noise due to the variability. So, but if you look, not all of these techniques are essentially statistical. So they are signal detection techniques based on certain hypotheses. And the idea was that actually Mickaël proposed me that, do you think one can try to derive some of this from statistical mechanics? So after some effort, I think we managed to prove this. So today I will talk about that. So the final result is that, just to make the sort of take-home message clear from the beginning, is that the optimal fingerprinting methods are very robust and sort of closely related to what we can say about the responsible system to perturbation via response theory. And B, in order to be improved, we need to be a bit careful in the definition of what is natural variability. Okay, so this is the main result. So now, I will need to go through some steps, because that hopefully will clarify the connection. So remember, of course, general setting, the climate is a multi-scale system, and with a lot of variability on a broad range of scales. And this basically makes the problem of signal detection very hard. And in fact, the separation of climate change, whatever it is, from climate variability, very non-trivial, because, one can say that, climate has always been changing. The problem is that one has to define what is the signal. And again, this requires some attention. We have to keep in mind that, of course, our measurements on this climate are far from optimal in any sense. They are improving continuously through a tremendous effort. But by definition, they are very sparse. They are very heterogeneous. We have, as an example, very small direct measurements of the deep ocean, which is on the slow scale the most important thing. And they change in time. And we don't really measure things. So in most cases, we have some measurement, we invert through models, and we relate this to the state of the system. That's the whole science of basically remote sensing, as an example, which is, of course, a huge enterprise by itself. And as we know, we take advantages of models that are very different, like Earth system models, intermediate complexity model, and toy models. And we use these models to, sort of understand the dynamical mechanism at different scales, to interpret the observations, and to try to make a sense of what we see. And last element to keep in mind is that when we, of course, when we try to develop theories of climate, we tend to have a dichotomy. On one side, we have stochastic theories of climate, like following the intuition of Hasselmann, and of course, such the Hasselmann program, one of the key pillars of the Hasselmann program is in fact the detection and attribution. So basically, how to separate signal from noise is, if you want, the inverse problem side of the direct problem of writing the climate equations, as in the left-hand side of this slide. of course, the problem that is not solved by sort of casting the problem as a stochastic differential equation is defining the nature of the noise. And as we know, the noise comes from the instabilities of the system at different scales. And this impacts the problem of what is the variability of the system. And so we will go back to this. So when we want to study the response of the system, of the climate system, as we said, as variability of multiple scales, and we can see this also as a response to forcing, and the climate sees smooth response to forcing, high sensitivity when we get close to tipping points, and then occurrence of tipping points, and transitions to competing states. And we observe all of this in our records. We are very scared of tipping points. And we have, of course, entire projects dedicated to this, hopefully future projects as well. We will need now, I will need briefly to go again through some of the aspects of response theory, because they will be useful then for understanding how we can interpret the detection and attribution problem. So please bear with me a little bit. So what we will have to do in the next few slides is to sort of, and this has come from the collaboration I've had and I'm having with Manuel Santos Gutierrez, who is also now at the Weizmann, and he was a student in Reading. So Manuel wrote a wonderful thesis, and there was something left out of the thesis that we decided it was time to dedicate some time on, and I think it was a good idea to do that. So the idea was to try to write in a sort of a general form response formulas for stochastic differential equations. And this was a case where if you rewrite things in a slightly more depending on your aesthetics, elegant way, you extract information that was hidden. So this was a lucky occurrence. So the idea is, if you start from a stochastic differential equation like here in the first row, you add forcing that could be either deterministic, so changes in the drift term or changes in the noise law. And this forcing can be time dependent. So you're considering the general case where you have a background state and you add some modulation in parameters or extra forcing or whatever it is. So clearly this has relevance for climate. Please note that one allows also for including stochastic perturbation, so changes in the noise. So that is actually in principle a bit new. So now you write this. This is a Langevin equation. You go into the Fokker-Planck representation, do a Fokker-Planck representation, so evolution of probability. You do some expansions, which are by itself very standard, and you end up with some response formulas, which again are a sort of slight variance of what is well known, but we will see this is actually, the fact that they are slight variant becomes very useful in a moment, where you write that whatever, if you choose an observable phi of your interest, you have that the linear response, so the change that's linear with the factor epsilon and gamma you see on the first row, can be written as a convolution product of a green function with the time modulation of the forcing, which is G for the deterministic and F for the stochastic component. So note that you have a formula for time-dependent noise, which is, again, not entirely trivial. Anyway.
Can I ask?
Yes.
So are there any sort of constraints on the G and P on sort of they're slowly varying?
No, G and P just need to be a finite variation. That's all thing you need. Okay. So G and P can be anything in principle. They will just reflect on the response as a part of the convolution. So the only thing you really need is that the G and P are finite variations, so you can always choose an epsilon and gamma small enough so that that term is small, basically, at all time. Okay, that is the idea. So anyway, and of course, this is, I'm not going into the details of the radius of expansion. So this is just in principle an infinitesimal perturbation theory. This is the validity of the quantitative ability is a separate story that I'm not going to talk about today. if not briefly, but we will see that this is in fact an implicit assumption of detection and attribution, the fact that responses are always linear, okay? So anyway, we will see this in a bit. So now what you write, as I said, let's focus now for the deterministic case for the change in the drift, but as I said, the same applies for the change in the noise. You get the green function as a causal form, so that's why there is this nice theta heaviside function, and let me see, yeah, this is this heaviside function here, and then you have an expectation value over the unperturbed state of these operators. So this is the evolution, unperturbed evolution of the observable phi due to the unperturbed evolution operator e to the SL0 transpose. L0 is the generator of time translation, and L1 transpose is the operator here, and this is the associated with the perturbative field G. Okay, so this is in fact, as it is written, is a very general form of the fluctuation dissipation theorem. So in this case, you can write a general relationship between fluctuations and response, but the formulas you get are not the usual Green-Kubo formulas, the sort of intuitive fluctuations. And this is made possible by the fact that the invariant measure is smooth because you are in stochastic setting. So you bypass a lot of problems of the deterministic chaos. But okay, that's it. Now, we need to take this theory, and merge it with another piece of another sort of direction of work that's due to Schmid, Mezic, Branton, Kutz, and others, which is the so-called Koopmanism. So Koopmanism is a sort of general strategy for studying the evolution of a nonlinear dynamical system by changing the angle on the problem. So instead of looking at the evolution in time of an initial trajectory, you lift the problem to studying the evolution in time of observables of such system. So in this way, you basically go from, in general, let's say, a finite dimensional space with nonlinear evolution to linear evolution in an infinite dimensional space, where the linear evolution operator is exactly at for time differences t, the e to the t L0 tau L0 transpose I mentioned before, which in this slide, which I took from Branton, is called KT. So basically, the evolution of observables is linear, and you have to think it, for those of you who have a background in quantum mechanics, it basically looks like the evolution of wave functions in quantum mechanics, which is a linear evolution. Okay? Doesn't mean that the problem is not difficult. So now the idea in the strategy of Koopmanism is try to estimate this Koopman operator, its eigenvalues and eigenvectors, and then re-expand, describe the evolution in terms of eigenvalues and eigenvectors of this Koopman operator. So this is the general strategy for doing model reduction. It's much used, especially originally a lot in fluid mechanics, but in many other fields as well. So now let me show you how we can use this. So what we do is we take that observable, that expectation value in the between parentheses here, and I expand these the evolution of my observable in eigenvectors of this Koopman operator, and so I will end, forgetting for a moment the residual, sort of a spectral decomposition of this operator in terms of projection onto the various eigenvectors and on the eigenvalues of this evolution operator. So just a spectral expansion. So by doing this, and under suitable hypothesis, I am now making the story a bit simpler, but the essence is here. I'm able to write this complex term, which looks untreatable, as basically in a very simple form. So what one has that in high degree of generality, this term becomes nothing but a sum of exponentials. So basically the green function in general, for very general system, are nothing but, apart from basically a heaviside distribution times of suitably weighted exponential. And the important thing is that this coefficient lambdas depend only on the background system. So do not depend on the observable and do not depend on the forcing. Whereas these projections, the constants, depend on the observable and the forcing. So these lambdas are universal. So are universal for a given system. And so as a result, we get that, and this applies both for deterministic and stochastic forcing. So basically, in general, we have this miraculous thing that apart from degeneracy and an extra term that I don't want to discuss today, this is the general form of a green function. So in some sense, we have that the general green function is a collection of damped motion, possibly oscillating and damped, because in general, these lambdas are complex, and so there is a complex conjugate pair. So this is in time. So basically, the response always looks like some damped oscillation or just damped motion. If we go into frequency range, and so these lambdas will be very important at the end of our discussion. But anyway, the nice result that you obtain by linking these two theories is that, in fact, very generally, the frequency Fourier transform of the green function is nothing but a sum of these sort of terms, which look like a collection of harmonic damped oscillators. So this is a sort of a quite interesting result, or if you want a boring result, because it shows you that the response, even for very general system, looks like a collection of harmonic damped oscillator, which actually is the same thing you get also in quantum mechanics, in classical mechanics, and now also in non-equilibrium systems. So a lot of things look, the linear response looks similar, but of course, what changes dramatically in this system is the interpretation and the meaning of this coefficient and of these constant lambdas. Still, that's is important because it can be used for data-driven methods, because we have it's a parametric problem in some sense. So now let me. I already talked in the past. So I want to honestly skip this, make this part very rapidly. Just I want to say that response theory can be used to study how the climate, at least the climate models, respond to perturbation. It's been used, it can be used to generalize the concept of climate sensitivity, to relate climate sensitivity and transient climate response. You can basically construct the climate projections on models of different level of complexity, simple model, intermediate complexity model. You can project global quantities as well as spatial fields by constructing green functions. You have to construct these green functions. This can be done by suitable experimental procedures. So this is a doable thing. So the problem is how you construct this green function. There are different methods. The easiest is to perform a set of probe experiments, derive the green function, and use it then to predict climate change to a second, to any, in fact, in principle, pattern of forcing. More recently, with Valerio Limbo, we applied this also on an actual Earth system model, and we managed to reproduce very well things, sort of quite quirky properties of climate change, like the cold blob in the North Atlantic, as well as the response of the thermo-island circulation and the Antarctic circumpolar current to CO2 increase. And we see, as an example, a great sensitivity of the thermo-island circulation, which indicates, and this can be made clear in a moment, the proximity of a tipping points that many people, including some members of our team in TIPIS, are studying in great care. So this is quite comforting. And something that has been done by other colleagues, including some people in our project, has been to look at the problem in a different angle. So basically, instead of focusing on computing the green function from experiment, has been on trying to identifying these lambdas. And because these lambdas describe basically the acting feedbacks of the system, the negative feedbacks of the system. So if you identify the lambdas, I'm able to learn really a lot about the fundamental properties of my system. So That's interesting because the lambda are associated to the natural variability of the system. As I said, it's the unperturbed are associated to the unperturbed Kopman operator, but they also describe the response. So that's another way to generalize the concept of fluctuation and dissipation. So, and this can be seen, as I said, the reconstruction of lambdas can be seen as a way to compute response or to provide a better characterization of feedbacks at different scales. Now, and Robin and Anna and Henk and others have done, I think, great work here. So now, linking up, so what is also interesting is that when the real part of this, one of these lambda gets close to 0, we have two phenomena happening at the same time. So we have that the decay of correlation of, in fact, a general observable becomes very slow, and the response of systems to perturbation tends to diverge. So we have a general mechanism to understand tipping points. And somehow what has become apparent is that the occurrence of enhanced sensitivity, very high sensitivity, the occurrence of slow decay of correlations, and the fact that the real part of one of these lambda becomes close to 0 are basically the same thing. And so this is a general way to describe tipping points. Now, so this is, and as an example, Alexis Tante in his thesis has been carefully studying this on an intermediate complexity model and proving that this framework holds well. So now, this is the sort of setting of a response theory for climate, and at least in the way I like to propose it. Now let's try to connect this to detection and attribution, and hopefully I will convince you that the link is very strong. So, as I said, very important, anything we say using these tools of statistical mechanics neglects, by definition, the individual trajectory. So in a statistical mechanical concept, the individual trajectory is immaterial. In some sense, it doesn't exist. It makes no sense. So this immediately tells you that statistical mechanical tools per se are not sufficient for understanding climate change as in the way it is manifesting itself in this individual realization of the universe. So if we had access to multiple realization of the universe and were able to take averages, then statistical mechanics will work. So statistical mechanics is not good for individual trajectories, okay? But instead, so that's a tool that's not sufficient for all problems. So the problem of detection of attribution tries to say whether the individual trajectory we are observing, we are living on, can be associated with the existence of some sort of trend in the climate system, and whether, that's the attribution part, such a trend can be related to specific forcings. So you see that there is a distance here. We try to bridge this gap. Okay, so detection has to do with the rejection of the null hypothesis. The observed climate is consistent with natural climate variability. So it tells us about the evidence of climate change. Attribution, it's a separate step, is to say whether the observed climate change signal can be plausibly and consistently explained by a given portfolio of external causes. Okay? So now, so as of IPCC, you have basically to follow a protocol like this. You choose certain variables. You want to estimate how certain external drivers to the forcing have changed in the past. And you want to investigate how this forcing can influence the climate. And then relate observations, which is what we are, what we are observing, with the effect of the separate effect of these potential causes. So we see that there is immediately a sort of separation between observation and potential impacts of different causes, which will require the application or the use of models. Okay, so technically speaking, you want to do the optimal fingerprinting boils down to this, and the idea is fundamentally due to Klaus Hasselmann. So we want to find the optimal solution in these variables beta of the following, of this multivariate regression problem. So yk is a vector of observation, change in the globe, in the surface temperature in certain at different locations, could be. The xm are the so-called fingerprints. So these are the definition of which is very non-trivial. Beta are the regression quantities, basically, and R is the natural, unperturbed natural variability. This is how things are custom. So these X are the basically, in a statistical mechanical sense, the expectation value of the change in the signal that we are interested in due to one of these M assumed causes, which could be increase in greenhouse gases, volcanic activity, land surface, methane, aerosols, and so on. Okay, so now these fingerprints are constructed using models, and usually by doing averages of the response of a given model, so through an ensemble approach, to each individual forcing. So I have a background state, I apply one of these forcing, say land use, I look at the impact of this, I repeat the simulation for a certain number of times, I take an average, and this will become the corresponding fingerprint. So now the problem is that I do this regression, and I try to see whether these beta are sort of consistent or not with the hypothesis that this cause is relevant in some sense. So this is how the thing fundamentally works with variance. An important aspect is that these fingerprints are not perfectly known because, of course, there is an uncertainty on them due to the fact that one, the model contains error. Second, since they are constructed using a finite set of model simulation, there is variability in the fingerprint itself. Sometimes these fingerprints are constructed by averaging the response of different models. And at the end, I hope I convince you that this is a very bad idea to do in general, okay? In the sense that it could give us some sort of misplaced optimism or misplaced certainty in what we get. So a key aspect of these optimal fingerprinting methods is the consideration of the so-called Pearl causality. So this is key because it allows us to make causal statement by comparing the world as it is with the counterfactual world that would have occurred had something else been implemented. So this is different from Granger causality, which basically has much harder time to disentangle causal relationship from pure causal relationship from correlations, and the Pearl causality requires the use of models and the application of interventions. The interventions are exactly the application of different protocols of forcing in an unperturbed, otherwise unperturbed climate run. So the concept of causality is key to making statements about the physical relevance of the causes. That's why we can do the attribution, okay? So remember, the attribution in this strong causal sense requires that we use models in a sort of a very organized way. So we run the model with only one forcing, and then with another forcing, and then with another forcing. And then we combine these results to construct the portfolio of fingerprints. So now, this optimal fingerprinting method is an optimization problem and can be solved. So in some cases, assuming the fingerprints are exact, there is a simple linear solution, and one can obtain a confidence interval for the betas. And if the betas are bounded away from zero, that means that you're basically, you can do the detection, and if confidence interval includes 1, you basically are able to say that the attribution is performed, because you are able to say that that cause has an impact different from 0, and with a weight possibly one on the final outcome. Okay, that's basically how it works, with lots of variants, which I'm not able to, or don't want to go into. Things can be more complicated by assuming uncertainties of the fingerprints, but and the procedure becomes more complicated. But still, at the end of the day, you get your best estimate for the betas, your confidence interval for the betas. This confidence interval depends a lot on the intensity of the natural variability, and this is the fundamental reason why doing detection of attribution when you have a lot of natural variability, it's harder, because you have a broader confidence interval for beta. That's it. That's why doing the detection of attribution on small regional quantities is harder than to do it on global quantities. And the result you get in a lot of studies, and this has been a mainstay of IPCC for now 20 years almost, is exactly an estimate. So associating anthropogenic forcings to observed climate change by doing this operation on fields, estimating the betas, and then in this way you can even ex post attribute a different fraction of the observed, say, change in the global average surface temperature to different causes. Methane forcing, CO2 forcing, land use change, aerosols, and so on. So you can disentangle different causes and say the relative contributions, okay, at local and at global level. So, and you can use it, so if you reaggregate, as I said, to deconstruct the temperature time series of the past according to the role played by different forcing. Of course, depending on the model you use to construct the fingerprints, you will obtain different results. So you can, this is the case, in this case, different models have been used and they provide broadly results that are in quite broad or quite good agreement. And so basically it tells you that each model, climate model, will tell you, of course, a slightly different story about the attribution of climate change. But coherently, as we know, human activities are responsible for observed climate change without a doubt. Now, okay, so that's the sort of the setting. And now let's go back to the formulas I have shown you before. So this is exactly the same as before, but now I assume I have U, say, deterministic forcings, and I have V, stochastic forcings. And now I write my response of my observable of interest phi, which will become, of course, the sum of the U responses to deterministic forcing and V responses to stochastic forcings. Now, where each of these terms has been computed using the green functions in the way I mentioned you. But, you know, I can also forget how this has been computed. I have that this is how I decompose my change in one observable. Okay, that's just rewriting what I wrote you before, just considering more acting forcing. Now I can just do some small change in this notation, and I say that I put this background climate on the reference date, if you want, on the left-hand side of this on this equation, and I get that the change in the climate, so in the expectation value of the statistics, is the sum of these m terms. Now I assume that U plus V makes m, so I put together, I clump together stochastic and deterministic forcing because it makes no problem to me. So that's the impact of all forcings. So now I can lift the problem from statements on expectation values to individual trajectory in the following very simple way. So basically, if I add to this term that I introduced before, the basically natural variability, to be understood in a second what it is, at time t, so which is my target time, it could be, you know, the second decade of the 21st century, it doesn't matter. I have that this signal, the signal is the sum of all these terms, which are due to the statistical mechanical forcing, plus, of course, the natural variability. And as you see, there is a pretty good relationship between this formula I'm writing you and the optimal fingerprinting equation that I showed you before, which was just conjectured on statistical basis, basically. So the idea is that making a relatively long story short, is that when you do optimal fingerprinting, you are assuming linearity in the response. And if you had a perfect model, so if you had the perfect model for the word, and if the response was exactly linear, you would just get automatically that all these betas would be 1. But of course, there is some discrepancy between true fingerprints and actual fingerprints of the real world, which of course you can't access directly. And you get that these betas in your estimate will not necessarily be centered in 1, apart from the uncertainties. So the fundamental idea is that if I do model fingerprint, if I do optimal fingerprinting between a model and its own output under the hypothesis that the response is linear, which is exactly what is behind these optimal fingerprinting methods, I would just get exactly this, all the betas are equal to 1. And there, what is left is the natural variability. So typically, in the optimal fingerprinting, this natural variability is taken as the unperturbed, is the variability of the system in the unperturbed state. And actually, this is a simplification because we know exactly what is this natural, so-called natural variability. So this is the variability that is associated to the fact that we have a non-trivial invariant, a non-trivial measure at time t. So this is the so-called, so this is associated with the properties of the so-called snapshot or pullback attractor, depending how you want to call it. I will not go into the details. So this is closely related to the discussion provided in the literature by Tamas Tell and collaborators on one side, Mickaël Gill, Mickaël Chekroun, Eric Simonet, and company on the other side. So the idea is that when you have a time-changing environment, you have that the measure changes, of course, and at each time, or in each time interval, it doesn't really matter, you get a variability that is changing with time itself. So, and this is the true variability that occurs in these equations here. So, in some sense, what we are learning as a result of these equations is that in the perfect model scenario, with perfect information, all betas should be 1, apart from uncertainty. Otherwise, one basically rescale the responses. But indeed, in the attribution method, you want to have the betas as close to 1 as possible. That is the reason. Okay. If I don't put all the causes, so I'm not, my attribution is incomplete, this will definitely cause biases in the estimate of beta, even in the perfect model scenario. And there is a nice link between the fundamental concept of causality that lies beneath the application of the optimal fingerprinting, which is this idea of causality a la Pearl, with, if you take the statistical mechanical angle, causality appears through the very form of the green function, which has causa, that is, the effect follows the cause. And so this is the sort of nice connection I see. Now, interestingly, so the fundamental message is that optimal fingerprinting for detection attribution can be understood on the basis of linear response theory for general stochastic dynamical system. And the fact that you can do linear response theory also for non-trivial observables, like extremes in principle, explains why you can use so flexibly these detection and attribution techniques. Now, the second part of the take-home message is that in the usual application of this optimal fingerprinting, the treatment of the natural variability is not fully correct because it is taken as the variability of the unperturbed state. And this is not correct. So this is, in fact, corresponds to doing a truncation in the equation. So one could possibly improve this optimal fingerprinting by basically adding fingerprints on the variability itself. So maybe maybe it will be worth trying to do this for improve the optimal fingerprinting methods. Nonetheless, we get that the whole strategies is correct. Now, final thing I want to mention is why it might be I think it's a bad idea to mix up fingerprints from different models, because the idea is that, okay, this is the usual idea of multi-model ensemble. I take one model, I estimate the fingerprints by doing ensemble average on the model A outputs, then I take another model, I get another estimate. Why not averaging them somehow? And I think it's a bad idea for the following reason, because each model will bring with itself the fingerprints, which, as I said, are constructed, in fact, are nothing but, if you believe in linear response. If you don't believe in linear response, you can't use optimal fingerprinting by definition. End of the story. So if you believe, so if you use optimal fingerprinting, you need to consider this setting. And this tells you that the fingerprints will depend dramatically, critically on the lambdas, on these lambdas I mentioned you before. So each model will have its own lambdas by construction, because the models are different, or in other terms, they have different natural variability. So if I mix model with different natural variability, and so with different lambdas, and I do averages of these fingerprints, I will do a horrible mess of putting together fingerprints that are associated with a sort of mismatching set of lambdas. So clumping together these lambdas will not give me extra information, will just confound the signal itself, because I might get a good, might be fingerprint for that observable for that time scale, but it might be totally wrong for another observable for a different time scale in my target problem, meaning that I make my problem much less robust. The problem becomes even more serious if I'm getting close to a tipping point, because if I'm getting close to a tipping point, either in the real world or in one model, in this case, one of these lambda will have a real part close to 0, and others won't. So I will basically, if I mix together models that are close to tipping points and models that are far from a tipping point, I get an information that is neither good for being close to a tipping point nor for being far from a tipping point, because I will get an extremely heterogeneous kind of behavior. A badly calibrated model, in that sense, will only degrade the information if I am trying to do optimal fingerprinting, so I'm trying to study in some sense climate change next to a critical transition. Okay, I'm done. Thank you very much.